The crew strapped in for this landing believe they are on a round trip. They are wrong. Everything that is about to keep them alive on Europa is the same thing that will make certain they never leave it. None of them can see it. Yet, for now, there is only the descent, quiet and slow, with nothing to do but watch. Europa rises to meet the crew, slowly, pale and enormous, until it fills every window with a light that seems to come from the ice itself. From orbit, it looked like polished porcelain. Up close, it resolves into something far stranger. Dark lines cut across the white in every direction, some of them running for thousands of kilometers, crossing and recrossing until the whole surface looks scored by a blade that never stopped. There are ridges, long fractures, wide flat plains of ice that stretch past the curve of the horizon and keep going. And it all makes sense. That is the first thing the crew notices. After months of studying orbital maps, the ground below actually looks the way it is supposed to look. The ridges sit where ridges should sit. The plains open up exactly where the data promised. Mission Control confirms the landing coordinates, reads the numbers back, and everything is clean. Then someone begins matching the landmarks below against the map by eye. Nothing lines up. The great fracture that should run north of the landing site is running to the east. The impact scar they chose as their reference marker is in the wrong place entirely, off by an amount that no instrument error could explain. The coordinates are correct. The map is correct. The surface is correct. Somehow, all three of those things are true at once, and the crew is preparing to land on a version of Europa that appears on no chart ever made. To understand how that is possible, you have to stop and ask a question that sounds simple, and turns out to be one of the most disorienting in the solar system. What is Europa really? Start with the part that feels comforting. It is a moon, a little smaller than our own, close enough in size that if you dropped it into Earth's sky, it would look almost familiar. But nothing else about it would. Its entire surface is water, frozen into a shell so smooth and so young that in places it reflects the faint, distant sunlight, like a sheet of glass laid over the dark. Stand on it, and the ground beneath your boots is not rock. It is ice, hundreds of millions of years of it, stretched taut across an entire world. And then there is the sky. Jupiter hangs overhead. And it does not hang the way the moon hangs over Earth. It dominates. From Europa's surface, the planet appears roughly 24 times wider than the full moon looks to us, a striped wall of cloud filling a huge portion of the sky, close enough that its storms are visible to the naked eye. It does not rise and set the way you would expect either. Europa keeps the same face turned toward Jupiter, always so from any single spot on the surface. That enormous planet simply sits there, fixed, watching, the way a mountain watches a valley. It is one of the most beautiful views a human being could ever stand beneath. It is also the first clue that something here is deeply wrong. Because that surface you are standing on, that seamless shell of ancient ice, is not attached to the world underneath it. Let that settle for a moment, because the mind resists it. On Earth, the ground is the planet. Dig down, and you hit rock, then hotter rock, then metal, all of it one connected body, turning together as a single object. When Earth rotates, everything rotates with it. The idea that the surface could be a separate thing, sliding freely over the interior, does not even occur to us, because here it is impossible. On Europa, it is the everyday reality. The ice shell, somewhere between 10 and 25 kilometers thick, sits on top of a global ocean of liquid water. Not lakes, not pockets. A single ocean wrapping the entire moon, kept liquid in the crushing cold by forces we will come to shortly. And that ocean does something to the ice above it that no solid planet ever does. It sets it free. The shell floats. It is decoupled from the rocky mantle far below, resting on water, unanchored, able to turn at its own pace, and drift in its own direction, independent of the world it belongs to. The surface of Europa is a lid on an ocean, and lids can move. This is not a fragile theory clinging to thin evidence. When scientists mapped the patterns of fractures across Europa, the way the great cracks bend and align, the arrangement of impact craters, the shape of the largest geological features, the numbers kept pointing to the same astonishing conclusion. The shell has rotated. The entire outer skin of this moon appears to have slid as one continuous piece, more than 70 degrees across the globe from where it first formed. 70 degrees. Take a moment with that number, because it is almost too large to feel. Imagine your spacecraft touches down at a place your map calls the equator of Europa. You step out. You plant your instruments. You log your position. And then you learn what that ground has done. The patch of ice under your feet, this spot you now call the equator, was once sitting near the pole. It has traveled the length of a quarter turn of the world, not blown there by wind, not carried by drifting continents grinding along over hundreds of millions of years the way Earth's plates crawl. It moved as one unbroken shell, gliding across a hidden sea, carrying every ridge and crack and frozen plain along with it, like passengers on a raft that spans an entire moon. The place has not just changed. Its address has changed. The very meaning of where you are standing has quietly rewritten itself, and it did so long before you arrived. And a migration on that scale does not happen gently. When something as vast as a planetary shell rotates over the interior beneath it, the ice cannot simply slide without complaint. It stretches. It compresses. It tears. And that violence left marks so large they can be read from orbit. Across Europa run enormous circular troughs, concentric arcs pressed into the surface, some of them reaching more than a kilometer deep, and stretching for hundreds of kilometers along their curve. For a long time they were a puzzle. Now they look like exactly what you would expect if a shell this size had torqued and flexed and dragged itself into a new orientation. They are stress scars. Wounds left in the ice by a moon in the act of turning itself inside out, geologically speaking, over spans of time we can barely picture. This is a frozen world. And yet, it is one of the most geologically restless places in the entire solar system. Not despite the ice, but because of what the ice is riding on. Now carry all of that back up to the crew, standing on the surface, staring at a map that refuses to match the ground. They are not landing on stable geography. There is no stable geography here. They are landing on a raft. The north their instruments point toward is arbitrary, a convenience, a line drawn on a world that does not agree to hold still. Their landing site is fixed to nothing beneath it, because there is nothing solid beneath it, to be fixed to only kilometers of ice, and then the black weight of an ocean. The coordinates in the flight computer describe a location. The problem is that on Europa, a location is not a place. It is a moment. It is where a piece of drifting shell happened to be when someone measured it. And it does not stop drifting just because people have arrived. Picture what that means over the long run. A habitat set down on the ice. Coordinates logged with great care. Flags planted, boots pressed into the surface. A small human outpost declared on another world. Leave it there. Come back in a lifetime, in a century, in the slow, patient time that Europa keeps. Those flags will have moved. The base will have slid across latitudes it never chose, its recorded position drifting further from the truth with every passing year, and no one will have touched it. The habitat will not have moved at all. The entire world will simply have slipped out from underneath it, quietly, continuously, the way it has been doing since long before the first human ever looked up and wondered what was out there. There is no such thing as a permanent address on Europa. You cannot own a spot on this moon. You can only borrow one, and the lease is written in ice that is already sliding out of your hands, which leaves the crew, and us, holding a question that only grows heavier the longer you look at it. If the ground itself is not tethered to anything, if the floor of this world floats and turns and carries everything on its back to somewhere else, then what does it mean to build here? What does it mean to land when the landing site will not stay where you left it? And harder still, what does it mean to leave, to lift off and return home, from a surface that will not even agree on where it is? But the drift is the smaller mystery. Because a shell does not float on nothing, and it does not slide for no reason. Something is holding that ocean liquid beneath 20 kilometers of ice, in a place where the sunlight is too faint and too far to melt a single crystal. Some force is pouring energy into this moon from the inside, enough to keep an entire sea from freezing solid. And whatever that force is, it is not gentle, and it does not only warm the water. It is the same force that keeps the ground moving. And it is about to become the reason the surface is one of the most dangerous places a human being has ever tried to stand. To understand what is warming that ocean, you have to look up. Jupiter fills the sky over Europa, and it is easy to think of it the way we think of the sun, as a source of light hanging safely far away. That is not what it is. Jupiter is not lighting Europa. Jupiter is gripping it. The planet is more than 300 times the mass of Earth.
And Europa circles it fast and close, completing an entire orbit in just 3.5 days. Locked in that orbit, the moon keeps one face turned toward its giant the whole time, the same way our moon keeps one face turned toward us. It never looks away.
But our moon orbits a modest world, at a comfortable distance. Europa orbits a monster from close range, and that changes everything. Here is the idea, stripped down to something you can feel. Gravity gets weaker with distance. So the side of Europa facing Jupiter is pulled harder than the side facing away, simply because the near side is closer. That difference in pull, across the width of the moon, is what a tidal force actually is. It is not one gravity acting on the whole body. It is a stronger tug on the front, and a weaker tug on the back, and the gap between them tries to stretch the moon along the line pointing toward Jupiter. On our own moon, that stretch is written into the rock as a permanent slight bulge, frozen in place, unmoving. The moon is rigid enough to simply hold the shape and endure it. Europa cannot. Its shell of ice, riding on that ocean, is not stiff enough to stand firm against a planet like Jupiter. So it gives. It flexes. And this is the moment the whole picture turns from beautiful to unsettling, because of one measurement. As Europa moves through its orbit, the distance to Jupiter changes slightly, and the direction of the pull shifts, and the tidal stretch rises and eases in a steady rhythm. Under that rhythm, the surface of Europa lifts and drops, not by a few centimeters. The solid ground of this moon rises and falls by as much as 30 meters with every orbit. 30 meters. 100 feet. The height of a 10-story building, breathing up and down, over and over, once every 3.5 days. Sit with the strangeness of that. This is not an earthquake. Earthquakes are sudden and rare and local. This is the entire surface of an entire world, swelling and sinking in a slow, patient, unstoppable pulse. It is not caused by anything breaking. It is caused by the sky. And it has been happening this way. This exact steady kneading of a moon-like dough in a giant's hands for billions of years, and it will keep happening long after everyone reading this is gone. This is not a poetic flourish. It is differential strain, calculated from physics and measured by spacecraft. The moon really does breathe, and that breathing is the reason there is anything liquid down there at all. When you bend something over and over, it heats up. Take a paperclip and flex it back and forth quickly, and the metal grows warm at the bend, warm enough to feel. Now scale that up to an object the size of a moon, flexing 30 meters at a time, forever. All that bending, all that internal friction, as the ice and rock grind against their own deformation, releases heat deep inside Europa. That heat has a name. Scientists call it tidal dissipation, and on Europa, it does something extraordinary. It is a furnace, buried inside a frozen world. Consider where this moon actually sits. Europa orbits at roughly 780 million kilometers from the Sun, so far out that sunlight arrives thin and weak, and the surface temperature sinks to around minus 160 degrees Celsius. At that cold, water is not a liquid. It is stone. Every drop of exposed water on Europa's surface froze solid ages ago. By every rule of distance and temperature, the ocean beneath the ice should be frozen straight through, a dead ball of ice from crust to core. It is not. And the only reason it is not is that constant tidal flexing, quietly pumping heat into the interior, holding back the cold, keeping an entire global ocean liquid, in a place where liquid water should be impossible. Take away Jupiter's relentless squeezing, and the ocean freezes. The furnace goes out. Everything that might make Europa interesting, everything that draws a human crew across the solar system to stand on its ice, exists only because this moon is being crushed and stretched, without pause. So the tides are a gift. They are the reason the mission exists at all. For anyone trying to actually stand on the surface and build something there, they are also a catastrophe. Think about what it takes to anchor a structure to the ground. On Earth, we sink foundations into bedrock, and trust that the rock will stay exactly where we left it. The whole art of building depends on the ground being a fixed thing you can push against. Foundations fail when the earth moves unexpectedly, when a fault slips or the soil shifts, and even small unexpected movements can bring a building down. Now imagine the opposite problem. On Europa, the ground does not move unexpectedly. It moves with perfect predictability. And it moves by tens of meters, up and down, every 85 hours, without end. You cannot plan around it because there is no still moment to plan for. There is no version of the surface that holds steady long enough to call it a foundation. To anchor a habitat here, you would have to bolt it to a surface that heaves the height of a building every few days, and keeps doing it for as long as the base stands. A rigid structure locked to that surface faces a brutal choice of failures. The tides will work at every seal until it flexes and fatigues, and finally lets the air out. They will stress every joint past what it was built to take. They will stretch and slacken every tether, cycle after cycle, until the metal remembers the bending and gives way. Anything stiff and firmly attached to Europa's surface will, in time, be pulled apart by a force it cannot resist and cannot escape. You might think the answer is to build something flexible instead, a structure that bends and floats and absorbs the motion, rather than fighting it. And that helps with the tearing. But flexibility opens a new set of dangers, just as deadly. A structure that flexes is a structure whose seals are always working, and a working seal is a seal that can leak, bleeding away the pressurized air keeping the crew alive. Every point that bends becomes a place where the deadly cold outside can reach in through the moving joint. The shielding that guards against radiation depends on staying intact and in place. And a hull that is always shifting is a hull whose armor is always being tested. Rigid structures get torn, flexible ones spring leaks, and let the cold and the radiation find a way through. The tides put you between those two fates, and never let you rest at either extreme. And the vertical heaving is only the first half of the problem. Because when you flex a shell of ice this hard, for this long, it does not simply rise and fall as one smooth sheet. It breaks. The same tidal stress that lifts the surface also tears it, and Europa's face carries the evidence everywhere you look. Across the moon run the lineae, long straight fractures in the ice, some of them stretching for hundreds of kilometers in nearly unbroken lines. There are ridges thrown up where the ice pushed against itself. There are regions called chaotic terrain, where the crust appears to have shattered into pieces, drifted apart, and refrozen into a jumbled surface that looks like a frozen sea caught mid-storm and held there. Some of these fractures may run so deep that they reach all the way down to the ocean itself. And here is the detail that should make a would-be settler go cold. These are not ancient scars from a long-dead past. We can tell, because of what is missing. Look at almost any old surface in the solar system, our moon, Mercury, the ancient highlands of Mars, and you see craters, thousands of them, the accumulated bruises of billions of years of impacts. A surface collects craters, the way an old wall collects marks. Europa is nearly smooth. It has strikingly FAGU craters, for a world that has been orbiting through the same bombardment as everything else. There is only one good explanation for a face that clean. The surface is being erased and remade. New ice is constantly replacing the old, healing over the impact scars, wiping the record clean. Some regions of Europa may be only tens of millions of years old, which in the lifetime of the solar system is practically yesterday. The ground is new, because the ground is alive. So put yourself back on the surface, inside that habitat, and understand fully what you are standing on. The floor beneath you is not rising and falling as one solid piece. It is also splitting, spreading in some places, pressing together in others, cracking open along lines you cannot predict, and refreezing over spans of time far longer than any human life. You are not standing on bedrock. You are not even standing on solid ground in any sense we would recognize. You are standing on pack ice on a planetary scale. Ice that lifts and drops with the sky. Ice that fractures and heals. Ice that could, along some fault you never saw coming, open beneath you. And this is the cruelty at the center of Europa, the thing that makes it more than just another hostile rock. The very force that makes this moon worth reaching is the same force that makes it impossible to stand on. The tidal flexing that keeps the ocean liquid, that lights the furnace, that creates the one warm sea in this frozen corner of the solar system, and the only reason anyone would come here at all, is the exact same flexing that heaves the surface, tears the shell, and guarantees that the ground will never once hold still. Europa offers a reason to come, and a reason you can never truly settle in the same breath. Its promise and its threat pour out of a single source, and you cannot accept one without accepting the other. Which raises the question that the cracks themselves seem to be daring you to ask. If the ice is splitting open, and some of those splits run all the way down to the ocean, then what is coming up through them? Because when spacecraft looked closely at those fractures, they found something no one could ignore. The cracks are not clean white ice. They are stained. Dark reddish-brown material runs along their edges and spreads out from their openings, as if something is leaking up from below and drying on the surface in the cold. Something down there is bleeding through, and what that stain turns out to be changes the entire story of what it would mean to live on this moon. Get close to one of those dark streaks, and the word crack stops fitting it. From orbit, the lineae look like shadows, thin lines of darkness laid into the white, as if someone had dragged a pen across the ice. But a crack is empty. A crack is a place where there is nothing. These are not empty. They are filled. Along their edges and spreading out from their openings, the ice is stained a deep reddish brown. The color soaked into the surface itself, and the closer you look, the clearer it becomes that this is not shadow at all. Something has come up through the ice and dried there. For a long time, nobody could say for certain what the stain was. Then instruments capable of reading the chemical fingerprint of a surface from a distance turned toward those discolored patches, and the answer came back in a form nobody could argue with. In 2019, careful spectroscopic analysis of one of Europa's chaotic regions identified the substance in the ice as sodium chloride. Table salt. Take a second with what that word means here, because it is easy to let it slide past. Not a compound that resembles salt. Not a chemical cousin that behaves a little like it. Sodium chloride. The exact same salt that is in the sweat on your skin and the water of every ocean on Earth, sitting in the fractures of a moon most of 1 billion kilometers away. And the way it is distributed, the mix of what is present, matches what you would expect if it came from an ocean that has been sitting in contact with rock. dissolving minerals out of a stony seafloor the way Earth's oceans do. Which tells you where it came from. It did not fall from the sky. It welled up from below. The ocean beneath Europa is not sealed away in some perfect vault. It leaks. Through the cracks that tidal flexing tears open, through vents where slushy water forces its way upward, along the same fractures that split the shell, ocean water has been pulled up toward the surface. And when it reaches the top, it meets the vacuum and the cold, and it flash freezes almost instantly, dried and locked into the ice. Then, over years and decades exposed to space, radiation slowly scorches it, darkening it to that reddish brown. What you are looking at in those streaks is frozen seawater from an alien ocean, brought to the surface and left to weather in the open. This changes the entire shape of the mission, and it does so in two ways that are each staggering on their own. The first is what it says about the ocean itself. We already suspected the water was there. Now we know it is salty, and a salty ocean is a talking ocean. Salt means the water has been touching rock, dissolving it, carrying minerals in solution. It hints that somewhere down on that hidden seafloor, water and stone are interacting, and on Earth, the most dramatic version of that interaction happens at hydrothermal vents, cracks in the ocean floor, where mineral-rich hot water pours out into the dark. Those vents on Earth are not barren. They are among the most crowded oases of life on the planet, whole ecosystems thriving in total blackness, fed not by sunlight but by chemistry. The salt in Europa's ice is a whisper that the same kind of chemistry might be happening beneath it, not proof of anything alive, but the ingredients, and a hint that they are being stirred. The second thing is more immediate and stranger, and it flips the whole engineering of the mission on its head. If ocean water is right there on the surface, frozen into the streaks, then you do not need to drill to sample the ocean. Think about what that overturns. The great obstacle of any Europa mission was always the ice, 20 kilometers of it, in places, between the surface and the water. Every plan for reaching the ocean had to reckon with the almost impossible task of boring down through that frozen shell, through kilometers of ice under crushing conditions, just to reach a single drop of the sea. And now here is the sea, or at least a scorched, refrozen memory of it, smeared across the ground where you land. You do not have to descend into the abyss to hold a piece of it. You can kneel down and scrape it off the surface with a tool in your hand. The ocean, the entire reason anyone crossed the solar system to get here, is lying on the doorstep. And this is exactly where Europa reveals that its cruelty runs deeper than shifting ground and heaving ice. Because the very thing that darkened those stains, the thing that made the ocean visible on the surface in the first place, is radiation. And that same radiation is what makes standing beside the streak a lethal act. Look again at the colors on Europa's surface, the yellows and the browns, and the deep rust of the lineae. It is tempting to read them as dirt, as grime, as some kind of mineral staining. They are not dirt. They are damage. Europa sits inside one of the most savage radiation environments in the solar system, and high-energy particles slam into the surface constantly, striking the ice, breaking apart the molecules, tearing water into loose oxygen and hydrogen, reshuffling the chemistry of everything exposed. This process, radiolysis, leaves its mark in the crystal structure itself. The colors of Europa's surface are the visible signature of relentless bombardment. The ground is not stained by material. It is stained by punishment. It is a chemical photograph of how hard this place is being hit. So the radiation is a revealer. It cooked the salt into visibility. It turned an invisible leak into a dark streak you can see from orbit and walk right up to. Without that bombardment, the ocean's fingerprints on the surface would be far harder to read. And it is also, in the same instant, the thing that will kill anyone who goes to read them. Here is the shape of the trap, laid out plainly. The ocean is the prize. It might hold the first life ever found beyond Earth, the single discovery that would change what humanity understands about its place in the universe. That ocean is now known to be reachable in two entirely contradictory senses. Its chemistry is right there on the surface, scrapable, sampleable, close enough to touch. And its actual liquid depths, the place where anything might actually be living, are still locked behind kilometers of ice that no one has drilled through. The crew can hold the ocean's salt in a vial and still be as far from the ocean's life as anyone has ever been. They can taste it without reaching it. And every minute they spend on the surface collecting even that frozen hint, the radiation that made the hint visible is pouring through their bodies. Stand there long enough to do the science, and the surface is killing you while you work. This is what Europa does. It gives you the ocean and denies you the ocean at the same time. It puts the greatest discovery in human history under your boots and separates you from it by a shell you cannot pass and a radiation field you cannot survive. There is no other place quite like it. On most hostile worlds, the prize is simply far away, or hidden, or hard. Here the prize is smeared across the ground in plain view, glittering with salt, close enough to scrape into a jar, and still absolutely, fundamentally out of reach. Hold the final image of it, a figure in a heavily shielded suit, kneeling on the ice beside one of those dark reddish streaks, a tool in a gloved hand, scraping a few grams of frozen brown material into a sealed vial. The sample in that vial is water from an ocean that has never seen the sun, older than every city humans have ever built, older than agriculture, older than the whole recorded story of our species. It rose from depths no human eye will ever look upon, froze in the vacuum, and waited in the cold for someone to come and collect it. And the act of collecting it, kneeling on that irradiated ground, is quietly delivering a dose that the human body was never built to take. They would be standing on the roof of an alien sea, close enough to know its chemistry by touch, forever sealed away from its depths. The ocean of Europa is, at the same moment, the nearest and the most distant thing in the solar system, and the crew sent to find it would feel both of those truths pressing down at once. Which forces the two questions that everything now hangs on. If that ocean is real, and salty, and stirred by warm chemistry against a rocky floor, then the first question is almost unbearable to hold. Could something be living in it, right now, in the dark, beneath the crew's feet? And the second question is colder and more practical, and it is the one that decides whether anyone ever gets to answer the first. Because the radiation on this surface is severe enough to reveal an ocean and lethal enough to kill the people studying it. So exactly how bad is it? Where does it come from? And what does it mean that the machines we have sent to explore this region are engineered, above almost everything else, to get in and get out before it destroys them? So how bad is it? Start with one number and let it stand alone for a moment before it means anything. 540 rem per day. That number is empty until you set it against a human body. So here is the scale. A person who absorbs around 100 rem in a short span begins to suffer radiation sickness, the nausea and the fatigue and the slow collapse of the body's ability to repair itself. Push toward 300 rem, delivered quickly, and, without medical treatment, that dose can kill. Those are the thresholds where the human machine starts to fail, and then stops. 540 rem is what you would absorb standing unshielded on the surface of Europa for a single day. Not over a career, not over a mission, over 24 hours. And it is not a total that creeps up on you slowly, a little accumulating each year, until decades later something goes wrong. It arrives every day, a fresh, lethal dose delivered daily. And then the next day it arrives again, and again, for as long as you stand there. A body left exposed on that ice would pass the threshold of sickness in a matter of hours, and the threshold of death in a matter of days, and the surface would simply keep pouring it on, indifferent, endless. Where does a storm like that come from? The same place everything on Europa comes from: Jupiter. The largest planet in the solar system spins fast for something so vast, turning once in only about 10 hours, and as it spins, it drags with it a magnetic field of staggering power, the strongest of any planet in our system. That field does something dangerous. It captures charged particles, electrons and ions, and holds them, trapping them in vast belts that wrap around the planet like invisible bands. Inside those belts, the particles are whipped around and accelerated to tremendous speeds, some of them approaching the speed of light, until the whole region around Jupiter is filled with a searing, invisible sea of radiation. And Europa orbits inside it. At roughly 670,000 kilometers from Jupiter's center, the Moon sits deep within the magnetosphere, well inside the killing zone, immersed in the belts rather than safely beyond them. It does not pass through this environment now and then. It lives there. Now stack the Moon's own defenselessness on top of that. Earth shields its surface with two things working together. It has a thick atmosphere that absorbs incoming particles, and it has a magnetic field of its own that deflects them, steering most of the danger away toward the poles. That is why life can exist on Earth's surface at all. Europa has neither. There is essentially no atmosphere to soak up the particles, and no protective magnetic field of its own strong enough to turn them aside. The trapped particles from Jupiter's belts slam straight into the surface, continuously, without anything to stop or soften them. The Moon stands naked in the storm, and every square meter of it is being struck every second of every day. If you want to understand just how seriously the people who build spacecraft take this environment, you do not need to read a safety report. You only need to look at how they designed the machine we sent to study it. Because there is one detail about that mission that tells you everything, and it is easy to miss. Europa Clipper does not orbit Europa. Sit with that, because it is stranger than it sounds. This is NASA's flagship mission to Europa, launched in 2024. A spacecraft built to study this moon in more detail than anything before it, carrying an array of instruments aimed squarely at understanding the ice, the ocean, and everything in between. It is entirely dedicated to Europa. And yet it will not enter orbit around Europa. It cannot. Instead, it orbits Jupiter, following a long looping path around the giant planet. And it approaches Europa only in brief passes, swooping in close, gathering what it can, and then racing back out to safer distance. Around 49 of these flybys are planned across the mission, and every one of them is a dart in and a retreat back out. Why build it that way? Why not simply park it above Europa and study the moon at leisure? because even Clipper cannot survive sitting in that radiation. Its most sensitive electronics are sealed inside a vault with walls of thick metal, a heavy armored box built for the single purpose of keeping the radiation out long enough for the instruments to do their work. And even sealed inside that armor, the spacecraft can endure only limited exposure before the particles begin to degrade it. So the flybys are timed in minutes. The whole trajectory is, at its heart, an escape plan. The mission approaches its target like someone reaching into a furnace to grab something and pulling their hand straight back out. Hold that image and then follow it where it leads. Here is a machine with no crew to protect, no life support to fail, no lungs to fill or heart to keep beating. It does not need to come home. It carries no children of anyone. It is wrapped in metal armor and asks nothing of the environment except that it survive long enough to take its measurements. And even that machine, stripped of every human vulnerability, cannot stay. It can only visit, briefly, before the radiation forces it to flee. Now put a crew on the surface. People who cannot dart in and out. People who must land, and stay, and work, for weeks or months, in the same radiation field that a robot built of titanium is designed to run away from. The machine flees, and the humans are asked to remain. That is the equation, and it does not balance. Bring the danger down to the body, because the number 540 means nothing until you understand what radiation actually does inside a person. It does not simply burn the skin like heat. It reaches through the body and tears at the machinery of the cells themselves. High-energy particles rip electrons from atoms as they pass, ionizing the tissue they travel through, and along the way, they shatter the strands of DNA that every cell depends on to function and divide. The cells that suffer most are the ones that reproduce quickly, the lining of the gut, the blood-forming cells in the marrow, the immune system, so those are the systems that fail first. It raises the long-term risk of cancer as damaged cells survive and multiply wrong. And it strikes at the central nervous system, the brain itself, the one organ you most need intact to survive a crisis. At 540 rem a day, this would not be a slow, distant threat. The acute symptoms would begin within hours: nausea, deep fatigue, an immune system falling apart, leaving the body open to infections it would normally shrug off. As the dose climbed, the mind itself could begin to falter, judgment and clarity eroding at the exact moment the crew most needs to think their way out of trouble. Over days and weeks, the accumulated dose would move past anything a human body can endure, and no amount of willpower or training changes the chemistry of a broken cell. So the obvious answer rises up: shield them. Wrap the crew in protection the way Clipper's electronics are wrapped in their vault. And shielding does work. Radiation obeys physics, and physics can be fought with mass. Put enough material between a person and the source, and the dose comes down. But that word, mass, is where the trap springs shut. Every centimeter of protection you add has weight, and in spaceflight, weight is the enemy of everything. More mass means more fuel to move it. More fuel means larger tanks to hold it, and stronger structures to bear it, and more powerful engines to push it. A heavily shielded ship becomes harder to launch off Earth, harder to slow down when it reaches Jupiter, and harder to lower gently onto the ice without tearing itself apart. Every kilogram of armor you add to keep the crew alive makes the whole mission harder to fly, and at some point, the ship becomes too heavy to send at all. Protection and possibility pull against each other, and there is no clean point where both are satisfied. And here is the part that stings. Because even after you pay that price, shielding does not make the radiation go away. It only reduces it. To bring the surface exposure down from 540 rem a day to something a human could actually survive over a long stay, you might need meters of material, meters of water, or packed regolith scraped up from the surface, or dense plastic like polyethylene, stacked thick around the living space. At that point, you are no longer building a habitat. You are building a bunker, a buried vault, a place to hide inside rather than a place to live. The crew's home on Europa would be a hole in the shielding, a small protected pocket in a world actively trying to get through the walls. And even the shielding turns against you. There is a cruel piece of physics here that most people never hear about, and it makes the whole problem worse. When a very high-energy particle crashes into a slab of shielding material, it does not always just stop. Sometimes it shatters atoms in the shield and produces a spray of new particles on the far side. Secondary radiation, X-rays and neutrons and gamma rays born inside the very material meant to protect you. In the worst cases, the shield itself becomes a source, and a crew hiding behind badly chosen armor can end up worse off than with less. Which material you use, how thick you make it, how you shape it, all of it matters, and getting it wrong does not just fail to help, it actively harms. Suppose you solve all of that. Suppose you build the buried bunker, get the materials right, avoid the secondary radiation trap, and give the crew a place where they can sleep and eat with the dose held down to something survivable. You have still not solved the mission. Because the whole reason to send people to Europa is not to hide in a hole. It is to go out, to explore, to sample those salt-stained streaks, to drill toward the ocean, to walk the ice and do the work no robot could. And the moment a crew member steps outside the bunker, all of that protection is left behind. A spacesuit cannot carry meters of shielding. Neither can a rover. You cannot walk around wearing a bunker on your back or drive one across the ice. So every hour spent outside, doing the actual science that justified crossing the solar system, is an hour of raw exposure. Another slice of that daily dose, absorbed directly into the body. The safe place is the place where nothing gets done. And the place where the work happens is the place that kills you. The mission's purpose and the crew's survival point in opposite directions, and every step outside is a withdrawal from a bank account that does not refill. And into all of this, add the one variable that no engineer and no crew and no mission planner can control: the sun. Every so often, without a reliable schedule, the sun hurls out a sudden burst of energetic particles. A solar particle event, a wave of radiation that comes tearing outward through the solar system, out in open space or on an airless moon, with no atmosphere to blunt it. Such an event can slam the local radiation far above its normal level in a matter of moments. On Europa, a surface already drowning in Jupiter's radiation, a strong solar event arriving on top of the baseline would be a disaster stacked on a disaster. And the worst part is the timing. There is no warning system that hands you hours to prepare, no siren that gives you the afternoon to get to safety. A crew might get minutes, perhaps only minutes, to recognize what was happening and reach whatever shelter existed before the spike passed through them. So imagine living like that. Not only bathed in a constant lethal dose that you plan around and shield against every single day, but knowing that at any moment, without meaningful warning, the sky could double the danger and give you almost no time to react. It is a threat with no season and no schedule, and you cannot watch for it, and you cannot outrun it, and mostly, You can only hope it does not come while you are outside. Return one last time to the contrast that makes all of this land. Europa Clipper will map this moon in extraordinary detail. It will photograph the surface, read the chemistry of the ice, chart the ocean beneath, and hunt for plumes venting into space. It will do all of it well, and it will teach us more about Europa than we have ever known. And it will do every bit of that while staying in constant motion, sealed in armor, alone, never once daring to stop and stay. Its entire design is built around the single principle of not remaining in the radiation any longer than it absolutely must. A human crew would be asked to do the opposite in every respect. To land instead of fly past. To stay instead of flee. To step outside instead of hiding in armor. To explore and drill and endure for months in the very radiation field that our most advanced machine was engineered above all else to escape. We built the robot to get out fast. We would be asking the people to hold their ground. And there is one more turn of the knife waiting in this, one that closes the space between the radiation and the ground itself. Because the radiation is not only a danger floating in the environment around the crew, it has been working on the surface for a very long time, striking the ice particle by particle, year after year, age after age. And a surface bombarded like that for millions of years does not stay smooth and simple. The same storm that would kill the crew may also have carved the ice they need to walk across into something no human was ever built to cross. The place they must stand on may have been sculpted, by the very radiation trying to kill them, into a trap of its own. Before a crew ever worries about the radiation, they have to solve a question that sounds almost trivial and turns out to be one of the hardest in the mission. Where, on all of Europa, do you actually put the ship down? There is a standard answer to this question, one that engineers have relied on since the first days of spaceflight. You land near the equator. The reason is pure physics. Any spinning world moves fastest at its equator, where the surface has the farthest to travel in each rotation, and that motion is free speed. When you launch from near the equator, the planet's own spin gives your rocket a running start, so you need less fuel to reach orbit than you would from higher latitudes. It is why so many crewed missions to our own moon aimed for equatorial or near-equatorial sites whenever the mission allowed. Land near the middle of the world, and leaving it later becomes easier. That same logic points a Europa crew straight toward the moon's equator, except Europa's equator may be a forest of blades. To understand what that means, you have to leave Europa for a moment and come back to Earth, to the thin, cold air of our highest mountains. In certain high-altitude places, on the slopes of the Andes and other great ranges, travelers have long encountered fields of a strange and beautiful formation. Tall, narrow spikes of hardened snow and ice, all leaning the same way, standing in dense rows like a crowd frozen in place. They are called penitentes, named long ago for their resemblance to rows of hooded monks bowed in penance, and walking through a field of them is like walking through a forest made of white blades. They form through a process that is quieter than melting. In the thin, dry air and strong sunlight, the ice does not so much melt as sublimate, turning straight from solid into vapor without ever becoming water. Small dips in the surface catch the light a little differently than the peaks between them, and once a hollow starts to deepen, it deepens faster, the sunlight carving down into the low points, while the high ridges between them survive. Over time, this runaway process leaves behind rows of tall, thin spires, separated by deep troughs. a whole landscape of standing blades. On Earth, penitentes reach a few meters at most, impressive to stand beside, tall enough to lose a person among them. On Europa, the model suggests something far larger. When researchers ran the physics of penitente formation for conditions on Europa's equator, the numbers came back sounding almost unreal. Blades reaching as high as 15 meters. 4 stories of ice, standing edge-on, spaced only a handful of meters apart, packed across the equatorial regions of the Moon below the middle latitudes. Not a scattered oddity here and there, but potentially vast fields of them. A spiked landscape covering the very zone a landing crew would most want to aim for. Why would Europa grow them so much taller than Earth ever does? Because Europa's conditions, strange as they are, turn out to be almost perfectly suited to the process. The Moon does receive sunlight, faint and distant but steady, enough to drive sublimation on the exposed ice, and then it removes everything that would blunt or erase the formations here on Earth. There is no wind to wear the spires down or knock them over. There is no rain to soften them and round their edges. There is essentially no atmosphere to scatter the sunlight and blur the angle at which it strikes. So the light comes in clean and sharp and carves with precision. Everything that keeps Earth's penitentes small is missing on Europa, and everything that lets them grow is present. The geometry is close to ideal for driving the blades to extremes. The scientists who modeled this did not present it as a curiosity. They flagged it plainly as a hazard to landing. You cannot set a spacecraft down on a field of blades. There is no flat ground between them wide enough to trust, no gentle surface to receive the landing legs, only troughs and spires and edges. And worse, this danger is one that might hide from the very instruments meant to find it. Radar sweeping the surface from orbit could show that a region is rough, that the terrain has texture and relief. But rough could mean many things. Radar roughness does not necessarily reveal the specific, deadly geometry of thousands of vertical knife edges standing close together. A landing site could read as merely uneven on the map and turn out, up close, to be impassable. Now, honesty requires a pause here, because this is not settled science, and the crew's fate hangs partly on which side of a real scientific argument turns out to be right. Not every researcher accepts that Europa's equator is a blade field. Some argue the Moon is simply too cold for sublimation to carve so aggressively, that its surface is too reflective, bouncing away too much of the weak sunlight to drive the process to such extremes, and that at Europa's great distance from the Sun, the energy available is too meager to grow blades of that size. The physics that predicts giant penitentes is plausible, and it is built on real principles, but it is a model, not an observation. No lander has ever touched down on Europa to look. Nobody has stood in that terrain or failed to. Until something physically reaches the surface and reports back, the fields of ice knives remain a serious possibility, rather than a confirmed fact. But sit with that for a moment, because the uncertainty is not comforting. It is its own kind of trap. The crew would not know until they arrived. That is the heart of the problem. High-resolution images taken from orbit as they approached might reveal the spires clearly, giving fair warning. Or they might not, if the blades are packed finer than the camera can resolve, hiding beneath the limit of what the instruments can see, so that a lethal forest reads on the map as smooth, pale ice. You could study your landing site for months from above, choose it carefully, commit your descent to it, and still not truly know whether you were dropping toward an open plain or a field of standing knives until you were already falling toward it. And now the trap closes fully, because of where all of this sits on the map. The equator is the place where launching home is easiest, where the moon's spin helps push you back to orbit and saves the fuel you cannot spare. And the equator is exactly where the penitente models predict the worst of the blades, the tallest and densest fields, clustered in those low latitudes. The single best place to leave from may be the single worst place to arrive at. Move away from the equator, toward higher latitudes, and the surface might grow smoother and safer to land on. But every degree you move costs you launch efficiency, making the eventual climb back to orbit harder and hungrier for fuel you do not have to waste. So the mission planners face a choice, with no good answer. Land at the equator, where leaving will be easiest, and accept the risk of descending into a field of blades that could tear the lander apart or trap it beyond any hope of takeoff. Or land at a higher latitude, where the ground might be gentler and safer to touch, and accept that escaping Europa's gravity from there becomes a harder, more fuel-starved problem than the mission may be able to afford. Safety in landing and ease in leaving pull in opposite directions across the surface of the moon. And there is no single spot that offers both. Picture the moment where all of this becomes real. A crewed lander drops toward Europa's equator, engines easing it down through the thin dark toward the pale ice below. From altitude, the surface looks smooth, a soft white plain stretching to the horizon. Exactly what the mission hoped for. The descent continues. At 500 meters, the ground begins to show texture, faint lines and shadows, roughness resolving out of what had looked flat, and someone aboard notes it and wonders. At 100 meters, the truth arrives all at once. The shadows are not surface markings. They are cast by towers. The whole landing zone stands revealed as a forest of ice blades, edge-on, 4 stories tall, throwing long dark shadows across the troughs between them, in the faint sunlight. There is no flat ground anywhere below, and there is no abort. At that altitude, that far into the descent, the spacecraft is already committed, already falling into whatever waits beneath it. That is the peculiar terror of Europa's equator. The danger is not loud. It does not announce itself. It hides inside terrain that looks safe from above, and only shows its real geometry when it is far too late to change course. And notice what this whole dilemma has quietly done. It has stopped being only about landing. The moment you ask where to touch down, you are already asking where to launch from. Because on Europa, the two are the same problem wearing different faces. Coming down is only half of it. The crew has to get back up. They have to leave this moon, climb off its surface, and begin the long journey home. And that is where the real trap of Europa is waiting. Not in the ice, and not in the blades, and not even in the radiation, but in what surrounds this little moon on every side. In the thing that holds Europa in its grip in the first place, and in the brutal arithmetic of what it would actually take to escape it. Suppose everything goes right. Suppose the crew survives the descent, threading down through terrain that might have been a field of blades and turning out not to be. Suppose the habitat holds against the heaving ice. Suppose the shielding keeps the daily radiation just low enough to live with, and no solar storm arrives at the wrong moment, and the drilling goes well, and the samples are collected, and the mission does everything it came to do. Suppose all of it works. Now it is time to go home. And the natural instinct is to think that this, at last, is the easy part. You have already done the hard things. Surely lifting off a small moon with barely any gravity is the gentle final step, the exhale after holding your breath. Here is the first surprise. Leaving Europa itself really is easy. Europa is small, and its pull is weak. Its surface gravity is only about 13% of Earth's, so faint that a person in a suit could crouch and spring and rise slowly into the pale light, hanging in the air far longer than any leap on Earth, drifting back down like something half-weightless. To actually break free of the Moon and reach orbit around it, you need a speed of only about 2 kilometers per second. Set that against Earth, where escaping the planet's surface demands more than 11 kilometers per second, and Europa looks almost welcoming. A modest rocket, nothing enormous, could carry a crew off that ice and up into orbit around the Moon without much trouble at all. But orbit around Europa is not home. It is not even close to home. It is a small loop around a small moon, and the crew circling in it is exactly as trapped as they were standing on the ice. Because Europa was never the thing holding them. Europa barely holds anything. The thing that holds them is the same thing that has been behind every danger in this entire story: Jupiter. To actually get home, the crew does not merely have to leave Europa, they have to leave Jupiter. And Jupiter is a well so deep that it swallows the whole system around it. From Europa's distance, the speed you would need to fully escape Jupiter's gravity is over 20 kilometers per second. Read that against the number from a moment ago. Escaping Europa took 2. Escaping Jupiter, from right where Europa sits, takes more than 20. It takes more speed to climb out of Jupiter's grip from Europa's orbit than it takes to leave the surface of Earth entirely. The little moon lets you go with almost no effort. The giant it circles does not let you go at all, without paying a price larger than leaving home ever cost. And in spaceflight, that price is not paid in effort or willpower. It is paid in fuel, and fuel follows a law that is merciless. The rocket equation, worked out over a century ago, describes how much propellant a rocket needs to change its speed by a given amount. And its central cruelty is that the relationship is not gentle and straight. It is exponential. As the change in velocity you need climbs, the fuel required to achieve it does not climb alongside it in step. It explodes upward. A small increase in the speed you have to gain can demand a huge increase in the propellant you must carry. And that propellant has mass, and that mass must itself be lifted and accelerated, which demands still more fuel to move it, which adds still more mass. The problem feeds on itself. Wanting to go faster makes you heavier, and being heavier makes going faster harder, in a spiral that punishes every extra kilometer per second far more than the last. Now lay out the full journey home, and watch the demands stack. First, launch from the surface of Europa into orbit around it. Easy, as we said, the gentle part. Then escape Europa's own gravity entirely, which is manageable, a moderate push. Then the enormous one, the climb out of Jupiter's deep well, the 20+ kilometers per second that dwarfs everything before it. Then, having escaped Jupiter, a further burn to set the ship on a transfer path toward Earth, across the vast distance between them. And then, at the far end, after all of that, the ship still has to slow down enough to be caught by Earth, rather than come screaming past it, which means either more fuel to break, or a perfectly judged plunge through Earth's atmosphere to shed the speed by friction, with no room for error. Every one of those steps demands velocity, and every increment of velocity demands fuel, exponentially. And every kilogram that has to make the trip, every crew member, every piece of the habitat, every precious sample of frozen ocean, every tank of air and drop of water keeping them alive. All of it has to be pushed through that whole sequence, and each kilogram of it multiplies the fuel needed, and each kilogram of that fuel demands more fuel to lift it. The arithmetic does not merely get hard, it gets monstrous. So the fuel has to come from somewhere, and there are only two ways to get it, and each one is its own nightmare. The first option is to bring it all from Earth. Carry every drop of the return fuel across the solar system, launch it, fly it all the way to Jupiter, and land it intact on Europa's ice, then simply keep it until the day you need it. Say it quickly and it sounds fine. Look closer, and it falls apart. You would be landing a fully fueled ascent vehicle, a heavy thing swollen with all the propellant for the journey home, and setting it down gently on a moon where landing anything at all is already a desperate problem. The heavier the return vehicle, the harder it is to lower onto the surface without crashing, and the more fuel you have to burn just to slow its descent, which makes it heavier still, the same spiral biting again. And then, having landed it, you would have to keep that fuel stable for months, in one of the most hostile environments imaginable, soaked in radiation that degrades materials, swinging through brutal temperature extremes, while you pray that nothing leaks, nothing freezes solid, nothing boils away into space. Every month it sits there waiting is a month it can fail, quietly, in a way you might not discover until the moment you need it and it is not there. The second option sounds smarter, and it is also almost unimaginably harder. Make the fuel on Europa itself. The idea has a name: in situ resource utilization, using what is already there instead of hauling it across the void. And on the face of it, Europa is the perfect place for it, because Europa is made of the raw material. Water ice is everywhere, an entire world of it. Split water into hydrogen and oxygen, and you have the makings of rocket fuel lying under your feet in unlimited supply. On paper, it solves everything. Then you look at what it actually takes, and the paper catches fire. To pull that off, you would need to build and run an industrial operation on the surface of Europa. You would need power, and a great deal of it, to split all that water. And power is exactly what is hardest to get here. Sunlight this far from the sun is thin and weak, so solar panels struggle. Nuclear power can do it, but a reactor is heavy and complex and its own engineering challenge to land and run. You would need the electrolysis equipment to break the water apart. You would need storage tanks built to hold hydrogen and oxygen as super-cold cryogenic liquids, without letting them slowly bleed away. You would need to shield every part of this machinery from the radiation that degrades everything it touches. And you would need all of it to run for months, continuously, without a serious failure, in a place where no repair crew and no spare part can ever arrive in time. That is not a backup plan you tuck away for safety. That is a factory, an automated industrial base that has to work, nearly flawlessly, in one of the most punishing environments any human has ever seriously proposed setting foot in. And the crew's only route home depends utterly on it succeeding. And suppose even that works. Suppose the factory runs, the tanks fill, the fuel is made. There is still another wall waiting, and this one no amount of engineering can knock down, because it is written into the motion of the planets themselves. Earth and Jupiter are both moving, endlessly, around the Sun, at different speeds along different orbits, and the distance between them and the geometry between them is constantly shifting. A ship can only make the journey home efficiently when the two planets are arranged just right, when a launch window opens, And those windows do not come often. They arrive on the rhythm of the planets, not the rhythm of human need. Miss one, for any reason, a delayed fuel batch, a failed system, an injured crew member, and the next chance may not come for many months, or longer. And every day spent waiting for that alignment is another day of radiation, accumulating in bodies and equipment. Another day of machinery, wearing down with no replacement. Another day of supplies dwindling. Another day of the mind grinding against the isolation. The wait does not pause the danger. It compounds it. And then, at last, when the window opens and the fuel is ready and the ship lifts off toward home, the crew faces the final cruelty, which is that going home means going back through the worst of it. To escape Jupiter, they have to fly outward through the same radiation belts that made arriving so lethal, the same searing region that even an armored robot was built to flee. But now, they are not the crew that arrived. They are worn down by months on the surface, their bodies already carrying the accumulated dose of everything they have absorbed. Their spacecraft is not fresh either. Its shielding degraded by the very radiation it has been fighting all along. And this time there is no turning back, no safe harbor to retreat to. The escape burn commits them fully to the climb out through the belts. If a solar storm should erupt during that passage, adding its sudden flood on top of Jupiter's constant assault, there is no shelter to reach, no bunker to hide in, nothing to do but hold course through it and hope the dose is survivable. Stand back now and see the whole shape of the thing, because this is where the truth of it finally settles. Europa's gravity barely holds you. You could stand on that ice and jump and float upward, drifting, almost free, and lifting off it into orbit takes hardly any effort at all. Leaving the moon feels like liberation, like the one easy step in a mission full of impossible ones. And it is a lie, because leaving the moon is not leaving. 670,000 kilometers out from Jupiter, orbiting far from the giant's cloud tops, you are still deep inside its gravitational prison, still gripped by a pull so vast that the whole distance to Europa is merely one of its inner corridors. Europa opens its hand and lets you rise. Jupiter never opens its hand at all. And that is the resolution the whole story has been climbing toward. The reason the first humans on Europa might never come home is not that they cannot leave Europa. Europa is generous. Europa lets them go. It is that they cannot leave Jupiter. The trap was never the little frozen moon with its floating shell, and its blades of ice and its bleeding ocean. The trap is the enormous planet that moon belongs to, the deep well they would have to climb out of, with fuel they may not have, through radiation they may not survive, in a window that may not come. They were never really imprisoned by Europa. They were imprisoned by the giant Europa has been circling all along, which leaves the last and quietest question of all. And it is the one that makes everything before it feel like a countdown. Suppose they cannot leave. Suppose the fuel does not come, or the window closes, or the factory fails. How long then does a crew survive on a world like this, alone, with no rescue possible and no way out? And what happens on that surface, so far from any help that help is not even a concept, when the first thing finally breaks? Somewhere in the habitat, months into the stay, someone gets hurt. Not a scratch, something real. A fall against a hard edge in the low gravity. A fracture, or worse, the kind of internal injury that bleeds where no one can see it. On Earth, this is a frightening afternoon, and then a hospital, and then, most likely, a recovery. It is survivable. People survive this every day. The commander opens a channel to mission control, describes the injury as clearly as fear allows, lists the symptoms, the vital signs, what has been tried, asks the only question that matters: what do we do? And then waits. A minute passes, 5, 10, 15, 20. Nothing comes back. Not because anyone on Earth is slow, not because anyone hesitated. 30 minutes pass in silence, with an injured crew member on the floor and a commander staring at a screen that will not answer. 33 minutes after the call was sent, it arrives on Earth. Mission Control hears it in the same instant it reaches them, and they respond immediately. The best doctors and engineers alive answering without a heartbeat of delay. And that answer, sent the moment they heard, then has to make the same journey back. Another 33 minutes, crossing the same emptiness in the other direction. By the time the commander hears a single word of guidance, more than an hour has passed since the call for help went out. And that is just one message each way. One question, one answer. The moment you need to ask a follow-up, to clarify, to describe how things have changed, you add another hour, and another. A conversation that on Earth would take 90 seconds stretches across an entire day, if it can happen at all. Real-time talk is simply not possible. It is not slow. It is gone. This is not a flaw anyone can fix. It is not weak equipment, or a poor connection, or a gap that better technology will someday close. It is the speed of light, and the speed of light is a wall. Jupiter orbits the Sun at roughly 5 times Earth's distance, about 5.2 astronomical units out into the cold. Even light, the fastest thing that exists, the thing that crosses from the Sun to Earth in 8 minutes, needs somewhere between 33 and 53 minutes to cross the gulf between Earth and Jupiter, depending on where the two planets happen to be in their endless circling. A signal cannot go faster. Nothing can. You could pour all the money and genius of the entire human race into the problem and not shave a second off it, because it is not an engineering limit. It is a law of the universe, and the universe does not negotiate. Sit for a moment with what that does to the very idea of mission control. On every mission humanity has ever flown, from the first capsules to the space station circling overhead right now, there has been a room full of people on the ground, watching the numbers in real time, ready to catch a problem the instant it appears, ready to talk a crew through a crisis second by second. That room is the safety net under everything. It is the reason astronauts can do dangerous things at all, knowing that 100 expert minds are watching their backs live. On Europa, that net is gone. Mission Control still exists, still watches, still cares as much as ever. But everything they see is old. Every number on their screens is a message from more than half an hour in the past. A photograph of a situation that has already moved on. They cannot watch the systems live, because there is no live. They cannot catch an anomaly the instant it appears, because by the time they see it, it is ancient history. They cannot talk a crew through an emergency in real time, because every word they say lands an hour late. The room full of experts is still there. It has just been pushed permanently into the past, always speaking to a moment that has already ended. Which means the crew is truly, operationally alone. Every decision has to be made right there, by the people in the room, in the moment, with no time to ask permission and no chance of live help. Whatever goes wrong, they answer it themselves, or it does not get answered in time. There is no cavalry. There is no one coming over the hill. There is only whoever is standing in the habitat when the alarm sounds. And that is only the operational side of it. The human side cuts deeper. Isolation is not new to spaceflight. Astronauts on the space station live apart from the world for months at a stretch. And it is hard, and it takes a real toll. But look at what they still have, even up there. They can float to a window and see Earth right below them, close and blue and impossibly alive, the whole world laid out beneath their feet. They can call home and actually talk, hear a voice answer in the same second they speak, share a laugh in real time with someone they love. They know that if the worst happened, rescue is only hours away. And every few months a supply ship arrives with fresh food and letters and small pieces of home. On Europa, every one of those comforts is stripped away. Earth is not a blue world beneath your feet. Earth is a star. One point of light among the others, so far away that you could cover your entire home planet, everyone you have ever known and everyone who has ever lived, behind the tip of a raised finger. There is no window that shows you home. Home is a spark in the dark that you have to be told which one to look for. And the people on that spark are living in a different time than you are. When you send a message to someone you love, they are already an hour further along in their life than the version of them you are picturing as you speak. If one of them falls ill, you will not know until long after the crisis has already broken, one way or the other. By the time the news reaches you, they may have recovered, or worsened, or the whole thing may be over, and there was never a moment when you could have done anything but wait. You cannot sit with them. You cannot help decide. You cannot even offer comfort in time for it to be comfort, because whatever you say arrives into a moment that no longer exists. You are sending words into the past and receiving words from the past, always reaching for a present you can never quite touch. There is a name worth giving to what this does, because it is its own kind of quiet destruction. Call it emotional lag. Human connection runs on timing. A real conversation is a living thing, built out of split-second reactions, the pause before an answer, the laugh that comes right on the beat, the way two people build a moment together in real time by being present in the same instant. Take that shared instant away, stretch every exchange across an hour, and the connection itself starts to come apart. You are no longer talking with your family. You are trading recordings with people who live in a different time frame than you do, each of you speaking into a void and hearing back an echo from a version of the other that has already moved on. Love does not need words to survive, but it needs presence, and presence is the one thing the speed of light quietly steals. Now carry that same lag back into the machinery, into a moment when something has started to go wrong, and watch how the delay turns from lonely to lethal. Here is the danger that most people would never think of. It is not the sudden catastrophe that makes the time lag deadliest. A sudden explosion is over before any signal could have helped anyway. The truly cruel scenario is the slow failure, the thing that goes wrong gradually, right at the pace where help almost matters, but never quite arrives in time. Picture a pressure seal in the habitat wall beginning to give. Nothing dramatic. A slow leak, tiny fractures spreading through the material that holds the breathable air in against the vacuum outside. The crew notices it. They are careful people, and they catch it early. They report it to Earth, describe the readings, and do the trained and disciplined thing, which is to wait for guidance from the experts. An hour later, the guidance arrives. Monitor the seal, it says. We are analyzing the options. Sensible words, Exactly what you would want, sent by good people doing their best. But in the hour it took those words to cross the void, the leak has grown. The situation the advice was written for is not the situation the crew is living in now, so they send an update, describing the worsened state, and settle in to wait again. Another hour. And the next guidance that comes back is built on data that is now 2 hours stale, answering a version of the problem that has already passed, while the real problem keeps moving. And now the crew stands at the exact fork this whole distance was built to create. They can follow the instructions from Earth, knowing those instructions were written for conditions that no longer exist. Or they can throw out the outdated guidance and act on their own judgment, right now, on the situation in front of them, and carry the full weight of whatever happens next. Trust the experts and act on old truth, or trust themselves and act alone. There is no third door. There is no waiting for a fresh answer, because a fresh answer is always another hour away, and the leak is not waiting. Whichever they choose, the fundamental fact does not change. They are alone. Earth can advise, but Earth is always describing yesterday. The decision, and the living or dying that follows it, belongs entirely to the people in the room. And this is the truth that would make this crew the loneliest human beings who have ever lived. Not because of how far away they are, distance alone is just a number. It is because they would be living in a different time than the rest of humanity, separated from everyone and everything by an hour that can never be closed. Earth exists. It is right there, a point of light they can see. Help exists, real and willing and expert. Home exists, with everyone they love still in it, and all of it, every bit of it, is permanently 33 to 53 minutes in the past, forever out of step with the moment they are actually in. They can see home, they can hear home, they can send their voices toward it and receive its voice in return, but they can never quite reach it, because by the time any of it arrives, the moment it was meant for is already gone. And that isolation, terrible as it is on its own, is only half of what makes it deadly. Because these are not people alone in an empty room. They are alone inside a machine, a habitat built of countless interlocking systems, power feeding life support feeding pressure, pressure feeding everything, each one leaning on the others to keep them alive. Alone would be survivable if the world around them were simple. It is not. It is a web of dependencies, any thread of which could snap. And the last and hardest question is, what happens on a world like this? With no help within an hour and no rescue possible at all, when the failure of one system reaches out and pulls the next one down with it. The mission does not end with an explosion. Hold on to that, because everything about how we imagine dying in space is wrong here. We picture the sudden blast, the hull breach, the single catastrophic instant. That is not how Europa kills. Europa does not need a disaster. It only needs 3 small problems, none of them fatal, and enough time for them to find each other. Watch it happen. The first problem arrives as almost nothing. A grain of dust, a fleck of fine debris, strikes a solar panel and damages a small part of it. That is all. There are backup panels. The system was built with margin for exactly this. Power output drops by around 12%, and the crew responds the way trained crews do, calmly and competently. They adjust the schedule, shut down a few non-essential systems, trim here and there, and carry on. By the end of the day, it barely registers as an event. A line in the log. Handled. The second problem is a person. One crew member develops an infection. Minor. The kind of thing a course of antibiotics clears up without drama on Earth. They have antibiotics. They start treatment. But this body is not an Earth body anymore. Months of radiation have worn down the immune system. Months of low gravity have changed how the body fights. So the infection, which should have faded in days, lingers. It hangs on longer than the medical guidelines predicted, and the crew member needs rest, real rest, which means for a while the crew is effectively down a person, still not fatal, still, on its own, entirely survivable. Just one fewer pair of hands. The third problem is a seal. In the water recycling system, one seal begins to show its age, stressed by the endless tidal flexing that heaves the habitat and by the constant swing of temperature as the moon breathes beneath it. It is not leaking, not yet. It is just showing strain, a warning rather than a wound. The crew does the correct thing. They order a replacement part. The replacement part will never come. There is no resupply ship. There is no next delivery. Whatever they brought is all they will ever have, and if the shelf does not hold the part they need, the part does not exist. Stop here and look at the three problems side by side. A slightly weaker power supply, one tired, recovering crew member, a seal that is worn but not yet broken. Any one of these, alone, is a Tuesday, a minor annoyance, something to note and manage and forget. On Earth, you would not even tell anyone about them. But they are not alone. They are in the same closed system, breathing the same recycled air, drawing on the same limited power, tended by the same shrunken crew, and now they begin to touch. The lost power means the life support system runs closer to its limit than it was designed to, with less room to spare. The sick crew member cannot do their share of the maintenance, so tasks slip, get pushed back, pile up. And the failing seal needs watching, careful, regular monitoring, which eats time and attention that the short-handed crew was already stretched to give. 3 small problems, and each one quietly makes the other 2 a little worse. Then the connections start to link into a chain. The reduced power puts strain on the environmental control and life support system, the machinery that keeps the air breathable, so it has to run longer cycles to do the same job it used to do easily. Longer cycles mean more wear on the filters and the pumps, parts grinding through their lifespan faster than planned. The crew, already down one person and stretched thin, begins to make the only reasonable choice available to them. They prioritize. They keep the critical systems perfectly maintained, and they let the secondary checks slide, just for now, just until things ease up. Sensible. Exactly what any of us would do. And in the checks they skip, a new problem grows unseen. A tiny crack opens in the housing of a carbon dioxide scrubber, the component that pulls the exhaled poison out of the air. And because no one is doing the secondary inspection anymore, no one notices. Now the chain stops being slow. That crack in the scrubber housing lets humidity seep in where it should never reach, into the electronics. Moisture finds a control board and causes a short. The backup system kicks in automatically, exactly as designed. And this is the part that feels like safety but is not, because the backup draws more power than the primary did. And power is the very thing already running short. So to feed the hungry backup, the crew has to take power from somewhere else, and they make another reasonable call. They reduce the heating in one habitat module, a module they can do without warming for a while. The colder module does what cold air does. Moisture in it condenses onto surfaces. The condensation reaches the seals and freezes there, and freezing water expands, and expanding ice presses against the seals and stresses them further. And one of those seals is the water recycling seal, the one that was already worn, already flagged, already waiting. The added stress is the last thing it can take. It stops merely straining. It fails. Water begins to escape. Not a flood, not yet, not an instant catastrophe. Just loss, steady and quiet. And here is the thing that a person on Earth, with taps in every room, can barely feel the weight of. In a sealed habitat, water is not just water. Water is oxygen, because you split it to breathe. Water is hygiene, the thing that keeps infection at bay. Water is temperature control, moving heat through the systems that keep everything in its safe range. Water is the substance the entire habitat quietly leans on in a dozen ways at once. Losing water does not mean getting thirsty. It means every margin, everywhere in the habitat, starts to shrink at the same time. And so the crew arrives at a set of choices, each one a door that opens into a new trap. They can ration the water, but rationing means less hygiene, and less hygiene means more illness. In a crew that is already sick, and already short-handed, and already fighting infections their bodies cannot properly clear. They can cut oxygen production to save water, but that lets carbon dioxide creep up in the air, and rising carbon dioxide means headaches and fatigue, and a slow fog settling over minds that need to be sharp. Or they can cut the heating further to save power for the water systems, but lower temperatures mean more condensation, and more freezing, and more stress on other seals. The same mechanism that just broke the last one, now aimed at the next. Every option solves one problem by feeding another. There is no move that only helps. And they are making these choices exhausted, sick, soaked in radiation that has been dulling their judgment for months, with the nearest expert advice sitting a full hour away in each direction, always answering a version of the crisis that has already changed by the time the answer lands. There is a name for what is happening to them, and it is worth saying plainly, because it explains why this was never really about any single part breaking. It is failure propagation. On Earth, most failures stay put. Your car's engine can die, and the radio keeps playing. The systems in our ordinary lives are mostly separate, so a problem in one place stays in that place. A closed-loop life support system is the opposite of that. In it, everything depends on everything. Power depends on the panels and the batteries. Life support depends on power. The crew's health depends on life support. Their ability to think and decide depends on their health. Maintenance depends on their decisions. And the integrity of every system depends on that maintenance being done. It is not a set of separate machines. It is a single chain where every link is holding up all the others. Break one link, and the load it was carrying shifts onto the rest, which now strain a little harder. Break two, and the spare capacity that was quietly absorbing the shocks is gone. Break three, and there is nothing left to shift the load onto, and the whole structure stops being something you can save. This is not pessimism. It is arithmetic, and the people who plan these missions know it precisely. They use a method called probabilistic risk assessment, which means, in plain terms, that they assign every component its real-world chance of failing, and then calculate how those chances stack up across the whole mission. For a short trip, the numbers stay comfortable. Few things have time to break. But stretch the mission across many months, and the math turns dark. Every extra day is another roll of the dice for every single component. And across enough days and enough components, the probability that something significant fails stops being a possibility and starts approaching a certainty. The longer you stay, the more systems must keep working perfectly, and the more chances the cascade has to find its opening. Now take everything this whole story has laid out, all of it, and set it down on top of this fragile, interlocking system. Because Europa does not just host the cascade. Europa accelerates it at every turn. The tidal flexing that heaves the surface never stops working at the seals and joints and structures, wearing them faster than any calm world would. The radiation that revealed the ocean and threatens the crew is also, all the while, quietly degrading the materials and the electronics and the human tissue that the whole mission depends on. The floating ice shell means the very ground the habitat sits on shifts beneath it, straining anchors and foundations that were meant to hold still. Fine dust works its way into mechanisms and grinds them down. The hour-long communication delay strips away any hope of real-time help when a cascade begins to run. No resupply means no replacement for anything that breaks, and no evacuation means that when the system finally becomes unsalvageable, there is no door marked exit. Every one of those is not merely a hazard sitting off to the side. Each is an accelerant, a hand on the scale, making it more likely that small problems find each other, and more likely that once they do, the chain runs all the way to the end. And so here is the truth. This entire journey has been building toward the thing that the floating ground and the breathing ice and the bleeding ocean and the radiation and the blades and the gravity well and the terrible silence of the distance were all quietly leading to. The crew will not die, because one great system explodes in a single moment of catastrophe. They will die because a solar panel cracks, which strains the power, which delays the maintenance, which lets a seal fail, which loses the water, which lowers the oxygen, which clouds the mind, which produces a single small error of judgment at exactly the wrong moment, during the ascent, during the one maneuver that has to be flawless, the launch that was supposed to carry them home. And the vehicle meant to bring them back to Earth comes down instead onto the ice of Europa. The first grave on Europa will not be dug by the radiation. It will not be dug by Jupiter's inescapable gravity, or by a field of ice blades, or by the ocean, or by the cold. It will be dug by a cascade, a chain of small, survivable, ordinary failures that no one could have predicted in that exact order, that the crew could not stop once it started running, and that no human being, alone and sick and irradiated an hour's silence away from all help, could possibly have survived. Not one disaster, 1,000 tiny ones, holding hands. Which leaves only one question standing, and after everything, it is the strangest question of all. If this is what Europa is, if the ground will not hold still, and the sky will not stop burning, and the planet will not let go, and the failures are written into the very arithmetic of staying, then why is anyone, anywhere, still drawing up the plans to go? So here is the honest answer. After everything, people are still planning to go. And it is worth understanding exactly what that means, because the word planning is doing a lot of quiet work. NASA is planning a Europa mission. That much is simply true. But it is not a crewed mission, not yet, not anywhere close. What is real, what is already flying, is the groundwork. Europa Clipper is out there right now, on its long looping path, built to map the surface in detail we have never had, to measure how thick the ice really is, to read the chemistry of the ocean from afar, and to hunt for plumes venting into space. If there is life in that hidden sea, Clipper might catch the faint chemical trace of it drifting up through a crack. Not a photograph of it, just a whisper that something is there. And beyond Clipper, there are ideas for what comes next. Landers, perhaps. Robots that could set down on the ice, test the radiation for themselves, sample the surface, and drill a little way into it to taste the chemistry just below. Machines, doing carefully and slowly what machines do best, in a place built to destroy anything that lingers. But a crewed mission is not the next step up from that. It is a different order of thing entirely, and it is worth walking through what it would actually take, so the gap is impossible to hide. You would need a spacecraft that can keep human beings alive across months of deep space, with life support that never truly fails. You would need radiation shielding heavy enough to bring the crew through Jupiter's belts alive, and small enough to still fly. You would need a lander that can survive Europa's surface and the endless heaving of its tidal flexing. You would need a habitat that can run itself, autonomously, for months, far past any hope of a repair crew. You would need power in a place where sunlight is thin and no resupply is coming. You would need to make rocket fuel out of Europa's own ice, at a scale that has never once been attempted. You would need an ascent vehicle strong enough to climb out of Jupiter's gravity well. You would need a path home that does not kill the crew with radiation on the way out. And you would need all of it, every single piece, working at once, without a critical failure, across a round trip measured not in weeks but in years. Every one of those things is possible in theory. Not one of them has been demonstrated at the scale this mission would demand. That is not the same as saying it is hopeless. We are not standing empty-handed. Closed-loop life support, the art of recycling air and water endlessly in a sealed space, is being tested and refined aboard the space station right now. Concepts for radiation shielding exist on paper and in the lab. Making fuel and oxygen from local resources has actually been done, in miniature, on Mars, where a small experiment called MOXIE quietly pulled breathable oxygen out of the Martian air and proved the principle is sound. Deep space habitats are being designed. Nuclear propulsion, the kind of engine that might make these journeys practical, is under development. But under development is not ready. It is a promise, not a possession. The distance between a principle proven in a laboratory and a system a crew can bet their lives on for years, hundreds of millions of kilometers from any help, is enormous, and pretending otherwise is how people die. Which brings the real question into the open, the one that sits underneath the whole endeavor. Should we send humans to Europa at all? Be fair to the question, because it has more than one honest answer depending on what you actually want. If the goal is science, pure knowledge about that ocean and what might live in it, then robots can do the work more safely, more cheaply, and without gambling a single human life. If the goal is inspiration, to stir something in people back home, then the images and discoveries Clipper sends back may already be enough to do it. And if the goal is simply to prove that humans can endure anywhere, to plant a flag on the hardest possible ground, then Europa may be the cruelest and least sensible place to try to make that point. But there is one goal that none of those answers can satisfy. If what you truly want is to search for life in person, with human hands and human eyes, to drill through that ice yourself, and descend toward an alien ocean, to stand on a world that has never once known sunlight, and look up at Jupiter filling the sky, and know that a living person is finally there to see it, then no robot will ever be enough. For that, and only that, Europa remains one of the most compelling destinations in the entire solar system. a place that calls to something in us that instruments cannot answer for. So the question was never really whether reaching Europa is worth doing. Something in us has already decided that it is. The question is whether we can do it without guaranteeing, from the moment of launch, that the crew will never come home. And that is where this has to end. Not with a verdict, but with a kind of sober respect. Because someday, perhaps, the systems will mature, and the engines will fly, and the shielding will hold, and the fuel will be made, and a crew will strap in for Europa despite all of it. If they ever do, they will be the bravest explorers in human history. Not brave because they are willing to go. Plenty of people are willing to go toward things they do not understand. They will be brave because they will go understanding it completely, knowing every single thing this story has laid out. They will go knowing the ground beneath them moves, knowing the moon breathes, heaving the height of a building every few days without rest, knowing the ocean they crossed the solar system to find will be right there, under their boots, and still forever out of reach, knowing the radiation is lethal and constant and invisible, knowing the surface where they must land may be a forest of blades taller than a house, knowing that Jupiter is a prison, and that leaving the little moon was never the same as being free, knowing that Earth is a point of light too far away to help, always answering an hour too late, and knowing that in a system this fragile, it will not take a disaster to end them, only a chain of small, ordinary failures, holding hands, running quietly to the end. They will know all of it, and they will go anyway. That is the part worth sitting with, long after the rest fades. Not the danger, the going. The strange, stubborn, magnificent fact that human beings, shown the full ledger of everything that could kill them, still lean toward the edge and ask when we leave. It is the same impulse that carried the first boats over the horizon and the first climbers onto the ice, scaled up now to the frozen shell of a moon around another world. The first humans to reach Europa will carry that impulse further than anyone ever has. They will stand on a floating shell of ice above an ocean older than our species, beneath a planet that will not let them go, and they will do the work, and they will reach for home. And they may never make it back. But they will have gone, and on a world that has waited in the dark since before there was anyone to wonder about it, that first set of footprints in the ice, slowly drifting across the latitudes as the whole moon slides beneath it, may be the most human thing that has ever happened anywhere in the solar system.